Thank you. Okay, it's gonna be weird because I have two devices in both of my hands, so I need to get used to that. So I might switch the microphone and the remote control. So, cześć, everybody. I still find Polish a little bit funny that you always sound cute and funny to us, and you greet each other with honor. So, my name is David. I come from the Czech Republic, from the city of Brno. I guess you know where it is. It's just a 4-hour drive from here. I work for a company called Red Hat. You probably heard about it. I work on a small Ruby project there. And I also do some research. Since COVID, I decided that I should do something with my life, and I wanted to do something interesting next to work. So I research how machines will trust each other in the future. We can talk about that later at the party, maybe. So, who studied computer science here? Hands up, please. Oh no. It's not gonna be new for you then. But my excuse is that Andrzej made me do it. If you know the big guy, the small on the picture, but the big guy of the conference. So, chapter 1, how computers work. Okay, so, sorry? Okay, so how computers work. Crash course for Ruby programmers. You have some instructions. I need to look closer to see them because some angel might reorganize some demon might reorganize my slides. So you have an instruction class, and there you have a pointer that every time you execute an instruction, you increase a pointer. Then you have instructions that are subclasses of these instruction class, such as jump, where you just set the pointer to an actual number, or you have classes like add, where you add the two operands and then yield back to the pointer by calling the super. It increases the pointer. Then you have subtract and other stuff as well. This is how a Ruby programmer would imagine how assembly looks like, or computer instructions looks like. The computer is just an iteration on those instructions. I'll give you some time. Okay, now everybody knows how computers work, right? So, chapter 1, let's talk about languages. Not these. Let's talk about languages with star. Let's talk about formal languages. And I'm sorry for bringing back your nightmares from the computer science classes. You're gonna relive that. Again, Andrzej made me do it. For the others, you might see something interesting. So, languages are consisting of alphabet. You use some kind of letters, same as in a normal language. In this case, you have digits from 0 to 9 and plus and minus. The words are a subset of iterations of these letters. So you do all the possible combination of the symbols, letters, and you take some of them. Let's say 1 plus 1 and 2 plus 2, 3 plus 3, 4 plus 4. These are, let's say, our language and doesn't contain anything. That's our domain. We work in that. Then there are some other formal parts called grammars, where you have a symbol and a non-terminal symbol. You iterate that. Then you have another non-terminal symbol. Again, a symbol or a non-terminal symbol iterated. That gets translated to a symbol and a non-terminal symbol iterated. Very complicated in a simplified way. Is it okay if I go further in front? Okay. So let's say you have an alphabet of 3 symbols. You have 2 non-terminals, D and O. And this is one rule of the grammar. The O translates to a plus. I guess it's easier to understand than this thing. Second one, the O can also translate to a minus, and the D can translate to either 1 and 2. This generates us a language that can do 1 plus 1, 1 plus 2, 1 minus 1, 1 minus 2, 2 minus 1. You know, you get the idea, all the combination. This is our domain. These rules set how our language look like. You can look into that later as a homework. So we categorize languages into different groups. The simplest languages are called regular languages. They usually have regular grammars, where the grammar is very simple. There you have a non-terminal symbol on the left, and on the right you have a non-terminal symbol and the symbol of the language, or you have a final symbol that translates to final non-terminal to translate into a symbol. It consists all the finite languages, and they are parsable by finite state machines. And one more thing, you can parse them by regular expressions with a star. So from programming, you know what the regular expression is. Anybody here who doesn't know what a regular expression is? You don't know it, or you know it? Okay. Nice that you read all of everybody's minds. Awesome. So basically a regular language for which you can construct a finite state machine. This one is taking any language that starts with A, it has infinite amount of A characters and ends with a B. Or in a regular expression, it's A plus B if somebody knows how to read regular expression. Anything else is outside the domain, it's not part of the language. Also, as I said, all the finite languages are regular because you can just write an automat that parses through all the possible ones, or you can just put all the combinations into one big regular expression. So the important part is whenever you write a regex in Ruby, it actually generates you an automat like this. That's how it's getting parsed. If you can look under the hood, you can check it out, and then you will know that I didn't lie. So more complicated languages are the context-free ones, where the grammar, on the left side, there is always one symbol, very important. And on the right side, you have a combination of terminals and non-terminals. That's not very important, it's an alpha. The important part is that on the left side, there is always just one non-terminal symbol. So you cannot create very crazy stuff. To parse it, you have to create a push-down automaton. This is basically a finite state machine and a stack. So you need some kind of memory. And there are two kinds of languages in this group. There are deterministic and non-deterministic. It's important that, if you want to have a palindrome, so let's say you have a lot of words like A, B, B, then its reverse is B, 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 A. And if you have a word like A, B, 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 A, according to this rule, it's part of that language. For that, you cannot construct a simple push-down automaton. But if you have a symbol in the middle, so you have A, B, B, pipe, B, B, A, then you can catch that symbol, and this automaton actually parses it. So the expression power, that's another important word, the expression power of a deterministic and non-deterministic context-free language is not the same. So it's a subgroup. During regular languages, determinism isn't important. Sorry for scaring the hell out of you who studied this and struggled with pumping lemmas in the university. In context-free languages, it is. Important part, you can construct a push-down automaton to parse it. Anything with parentheses. So whenever you have, even in your editor, you have parentheses, and you are checking if the parentheses are okay. The number on the left is the same, the opening parenthesis and the closing parenthesis is the same. You can write a push-down automaton to check it, because you put all the left parentheses to the stack, and whenever you close the parenthesis, you take it out from the stack. I guess it's easy. Then there are context-sensitive languages. Important part here, the grammar has more than one symbol on the left side. The rest is not that important. You can generate any kind of craziness with this grammar. For parsing it, you can parse it with a linearly bound automation. Yeah, linearly bound automation, which is a Turing machine with a finite space, tape. So it's really close to what we call computers because it has finite amount of memory. And I will show you in the next slide what Turing machines are. So there are recursively enumerable languages. These use unrestricted grammars. Everything is allowed. You can parse them obviously by a Turing machine, and you can also describe them by general recursive functions and lambda calculus. If anybody studied these math terms, these are equivalent, so you can always construct a lambda calculus for your Turing machine or generally recursive functions. So, Turing machine. You probably, who hasn't seen the movie with Benedict Cumberbatch? Imitation Game. Sorry? Hasn't. Good. Okay. You don't learn anything about Turing machines there, but so you have an infinite tape, and it has a head, and the tape has an alphabet, its own. Then you have a read-write head that moves on the tape. It can read and write and move left or right. It has states, and it has some transition function based on the symbol on the tape and the current state. It can move to another state, write another symbol to the tape, and move left to the right. I guess it reminds you of a computer in a simplified way. There are the stuff I just explained. I'm sorry I didn't see it. It's pretty complicated. It's a mathematical model of something much more powerful than the computer. The biggest difference is that you have an infinite tape. In a computer, you cannot have an infinite tape, obviously, because we have finite memory. So, important things with Turing machines, they don't use them for computing anything. They are used for mathematical proofs. One machine can simulate another. I guess that's a pretty long proof. We will not go into that. Sorry for anybody who's interested in that. Determinism isn't important. Non-deterministic Turing machine can simulate a deterministic one, and the deterministic one can simulate a non-deterministic one. It just takes longer time. So determinism here, you try all the combinations if you want a simple answer. You can also do multi-tape machines. And multi-tape machines can be simplified to single-tape machines, which was the proof that you can actually construct a computer with single kind of memory. Historically, you had two memories, usually, even in assembly. If you do x86 assembly, you have two kinds of memory in your computer. There is the code segment and the data segment. But physically, they are in one space, the same way as Turing machine can handle two tapes simulated on one tape. It's the same thing happening in computers. So there is a mathematical proof that computers can exist. Yeah, we cannot construct them in real life, unfortunately. And as I said, we use it to prove stuff. And there is something called Church-Turing thesis. It's basically saying that whatever can be expressed with Turing machines or its equivalents, like lambda calculus or partially recursive functions, can be mathematically computed. So whatever the Turing machine cannot compute, you don't have to run it, you just have to prove it that it cannot compute. It's not solvable by our current state of mathematics or algorithms. There's also one thing called the universal Turing machine, which is a machine with two tapes. One tape has the code, the other tape has data, which can you again join into one tape and get very similar something to a mathematical model of a computer that can be used for other proving stuff. Hope I didn't destroy anybody's brain by explaining these things, but when I teach my students at the university, I do believe that recognizing patterns is important. So in the next chapter, no, not yet, sorry. Before we go to the next chapter, there is another thing I want to talk about, is algorithmic complexity. There is two kinds of algorithmic complexity, space and time. Not that kind of space and time, but in the perspective of Turing machines, spatial complexity of an algorithm is how many pieces on the tape you use. In time-wise, how many movements you do on the tape. So if you are able to move your algorithm to the Turing machine domain, you just have to do these two calculations to know if your algorithm is quadratic, linear, in space or time, whatever. And again, pattern recognition. We're gonna go through how compilers and interpreters work. So when you write your code, it goes through a ton of stages in your Ruby interpreter. So first we do lexical analysis, then we do syntactical, semantical, we generate some intermediate code. These three are overlapped. Then there are some optimizations, and at the end we do execution. Compilers do code generation. So when you do lexical analysis, you read characters one by one. And here is important that you have some pattern recognition skills. This is a regular expression. This is as well. This is as well. So I guess it's easy to see that this is a finite state machine for language type 3. Right? Okay. Okay. Recognizing patterns. Then there's syntactical analysis that I won't show because it wouldn't fit on the slide. And I don't want to spin through like 5 slides. Basically, we parse these tokens and we construct some kind of internal representation, which doesn't necessarily happen in this phase. But from the tokens, you generate some kind of tree. In case of Ruby, you create an abstract syntax tree, which has instructions. Usually the top of the tree is an operation, and on the side you have the operands. There are other ways of internal representation creating in this step, but the most famous lately is bytecode. So like Java stuff, in some cases doesn't generate AST, but goes through a bytecode depending on how you configure it. It's not that important. Next one is, and that's where you get the syntax errors. So if it doesn't go through, then you see the syntax error in your interpreter. Next one is called semantical analysis, where you usually check if your code actually has a meaning, semantics. So type coherence, scopes and declarations, like your variable is defined in that moment, you're not overriding a constant, things like that. Basically logical analyzation. They mainly do that by going through graphs. You have a tree, you can traverse that tree multiple times. It happens plenty of times in any programming language. Yeah, and also Rust has its own famous fancy checker for errors. It's done in this stage where they actually do the memory checks and they claim that they can write super safe code. And next thing is optimization. I have some examples. So constant folding, you see it on the top. When you have a multiplication in your code, the compiler or interpreter can actually multiply it in advance and store it in the AST as this. So it doesn't have to do the multiplication later. You can make it fast. Same with constant propagation. If you have an A and 3 times A in B variable, then it can just write 3 times 3 and avoid the constant calling, basically flattening your tree a little bit. Then there is caching. You have a multiplication with a number. You can pull out that number into a constant and do the multiplications 1 and do the adding once and multiply it 10 times. Of course, I mean, you can also write it on your own, but if you do this, actually this happens under the hood. So you don't do the adding multiple times, just the multiplication. Loop unrolling is my favorite, and I actually implemented it at the university in hardware. So when you have MMX or SSC capable CPUs, which is most of our processors currently, then it's faster to do 4 instructions. It's possible to do 4 multiplications at the same time. So instead of going through one by one through this 1 to 256 and multiplying a number by 2, the compiler can actually detect the interpreter can actually detect that your CPU has MMX or SSC instruction set and unroll your loop into 4 multiplication. And these 4 multiplications happen at the same time, which can be pretty fast. It looks like it's slower, but it's actually 4 times faster because it runs in hardware. So the optimization's job is to use your hardware to the fullest. And if you remember from the beginning how computers work, then this code will be very easy to understand. So the interpreter is just going through the instructions and runs them, obviously. And if you compile it, you write them to a file in assembly. Assembly is the machine instruction set for a CPU, and then it runs through an assembler and it becomes bytecode. So there is one more piece that I didn't mention yet. It's called the virtual machine. It's not a virtual machine in the sense as you run it on VirtualBox or Parallels. It's very similar. You have a machine, when you have something that can run instructions that don't run directly on the hardware, you already have a virtual machine. And the purpose of this virtual machine is to run through this intermediate representation, sometimes directly on AST, sometimes on tree address code or bytecode or whatever. It's an abstraction to run it in multiple platforms. And good thing is that you can take this virtual machine and swap it to other languages. It can support stuff like just-in-type complication. In the case of Ruby, even garbage collection is imported in it, and parallelism management isn't, but the global VM lock, you probably heard it, that's killing parallelism in Ruby, is actually in there. So, some examples. The most famous for you is probably the YARV, yet another Ruby virtual machine written by Koji. Actually, it's a stack-based virtual machine implemented, and it optimizes and executes your Ruby code under the hood. So, next chapter. I have a really bad news for you. You probably will never do this in your real life manually. Even though they are patterns and these things are available and you can always do it, there are tools to generate lexers and parsers. You can describe the grammar of the language and run those three tools, and it generates you a parser. The thing that gets you ASTs or some kind of internal representation. Then you can just translate it to some bytecode or whatever you want, and then virtual machines are also available. You can use the Java VM. It's already existing as JRuby. Hi, Charlie Nutter. There is Graal VM, Truffle Ruby, which is, again, an alternative implementation. So we generate code for that VM. There is LLVM for Ruby News. And there are, of course, many more like Parrot, .NET, and others. So when you hear these names, that they are compatible with Ruby, they are, but they are running on a different virtual machine that has maybe better or worse performance, depending on the context. Creating a programming language like this is not fun, but but I think you saw the patterns, that we use some theoretical informatics and we use those patterns to be able to create a language. Like syntactical analysis is using push-down automatons and finite state machines. Semantical analysis uses graph traversal. These are things that you already do. So it's always nice to understand how these things work under the hood. And thank you for having me.
Okay, any questions?
Sorry for triggering bad memories from university. I saw in Michael that...
I think we just understand everything and we trust you. Okay, thank you very much. Big applause for the lead.